All right, so we were talking yesterday, kind of pick up where we left off, let's remind ourselves where we were. Start off by telling me what is the limit definition of a derivative, slope of the tangent. Limit of what? Okay, so we're going to do, we got two ways of doing this. Let's write it both ways. So we've got, what's the first way we talked about? Maybe the more standard way. F prime of x equals limit of what? We're going to use the delta x definition. Good, minus. Good, okay. So that's one way to write the difference quotient. The way we talked about yesterday, an alternate way was what? F of x minus f of c over as x approaches, good, as x approaches c. Okay, and what we were really looking for here was we started to compile a list of the kinds of places where derivatives don't exist on a function, okay, where tangent lines don't make sense, so we can't have a slope of a tangent line. Okay, and we came up with one yesterday, which was this kind of a place. We used an example of a greatest integer function, and we found that at any integer on a greatest integer function, derivative is undefined. How come? Who said that? I heard a bunch. Somebody help me out here. Who was talking over here? Breaking the function. Good. They're breaking the function. So what breaks down about our limit then? Or about our derivative, sorry. What doesn't exist there if there's a break in the function? The limit. Yeah, the two-sided limit doesn't exist, right? We ended up getting different results for the left-handed limit, or the limit from the left and the limit from the right. Agreed? And because we got different values for the limit doesn't exist, so the derivative can't exist. Okay? How about, let's look at a different example. Let's take an absolute value function. Let's look at this one. So this is another great opportunity for some review. How do we define an absolute value function? There's a couple ways we can define an absolute value function. Absolute value of x. How do we define it as a single function? Anybody know? What is the definition of an absolute value function? What's the job of an absolute value function? I put in a value and it guarantees the output is, well, non-negative. It could be 0, right? Okay, how could we build a function that does that? What do you think? Is there anything you know of that turns something, if it's negative, turns it positive? Squaring it does, doesn't it? Right? Okay, so I know that if I square something, it ensures that it's positive, but I can't change the magnitude of the input. If I input a -3, I have to get back a 3. If I input a 4, I have to get back a 4. Squaring it changes the magnitude, so how do I resize it back to square root? That's it. That is the definition of absolute value of x. And it works, doesn't it? Right? If I plug in a -3, well, -3 squared is 9. What's the square root of 9? Okay, good question. Is the square root of 9 plus or minus? There's another thing we've got to talk about. All this stuff comes up. What's good stuff we've got to talk about? So, the square root square root of 9 is exactly 3. Not plus or minus 3. The square root of 9 is exactly 3. Where does the plus or minus come in? Plus or minus comes in here. Stuff's all related. If I solve the equation, let's say x squared equals 9, what's the answer?
Plus
Well,
or minus.
plus or minus, right? Where does the plus or minus come in? We always know that if we take an even root of both sides, we got to put in a plus or minus. Did you ever, Algebra 2, probably talk about the missing steps there, though? Okay, this is important. The missing steps. What would I do to isolate x? When I isolate x, this is all in the context of algebra. Algebra 2 is so big for calculus because it really gives you all the modes of thinking that you extend in calculus. When you're isolating a variable, what direction do you use order of operations? Remember, if you're just using regular simplification, you go top down. But if you're isolating or solving, you go bottoms up, right? Okay, so then if we're going to isolate x squared, this is pretty simple. There's no addition or subtraction. There's no multiplication or division. We get up to exponentiation. How do you undo exponentiation? Square root both sides, don't you? Right? So then we would get the square root of x squared equals the square root of 9. Right? Well, what's the square root of x squared? No. Absolute value. Absolute value of x equals 3. When you solve an absolute value equation, what do? You isolate the radical and then what? You got to set it equal to both the positive or the negative values of the constant, right? So here's where we end up getting x equals 3 or x equals negative 3. Okay? That's where that plus or minus comes in. The square root of 9 is just 3. Okay? So in this case, if we evaluate the absolute value of 3, or negative 3, for example, we're going to get the square root of positive 9, which is just plain old 3. Okay? All right. So that's one way to do it. That's one way to write it. We're going to write it a little differently. Okay, we're going to write it as a piecewise function. That's more convenient for us, right? It's more convenient because we can see that the behavior of the function changes where? At 0. At x equals 0, 0, 0, 0, 0, right? So we could write an absolute value like this. We could say the absolute value of x equals what behaviors? What's one behavior of the function? If we're going to go from negative infinity to positive infinity, what's the behavior for this part of the function? But what's I mean, how would you, what's the definition of that line right there? Y equals negative x, right? So we get y, the absolute value of x equals negative x whenever what? X is less than 0. Good. Okay. What about at that one point in between? Okay, absolute value of x equals 0 when x equals 0, and it equals what over here? Function is defined as what? X. Good. Y equals x when x is positive value, right? Okay. So there's our function. So now if we want to calculate a derivative, well, we're just going to use, here's our formula, right? This is the function. This is f of x. Okay? So what's that going to look like? So we start general. So how about if we approach from the left first? Okay? So we have to figure out what this is. We have to figure out what is the limit of the absolute value of x minus, well, minus the absolute value of c, we'll say for now, over x minus c as x approaches c. What is that? Okay, well, let's take the limit from the left and the limit from the right, and if they agree, then the limit is defined. Agreed? Okay, if they don't, then the limit is undefined and the derivative can't exist. Okay, so what is then, let's take the left-handed limit first. What's the limit of, let's get specific here, we have the absolute value of x minus the absolute value of 0 over x minus 0 as x approaches 0 from the left. Everybody agree that matches our picture? Okay. So what's absolute value of 0 is just 0, right? So we end up with the limit of the absolute value of x over x as x approaches 0 from the left. Hey, what's up? Yeah, that's all right. What's up? Yeah. Okay. Oh, okay. I'll get her hooked up. Well, we had 2 for you. Yeah. Yeah. All right. But okay. So what does this equal then? When I have negative values of x, you guys told me that the absolute value of x is defined as that. Right? Does that make sense? So as x approaches 0 from the left, it's negative value, isn't it? Right? So then this looks like the limit of what? What's on the top? Negative x over x as x approaches 0 from the left. That is 0 over 0, isn't it? But that reduces to negative 1, doesn't it? Okay? Make sense? Okay? How about the limit? You can probably already anticipate what's going to happen here. If we take the limit from the right, we get the limit of the absolute value of x minus the absolute value of 0 over x minus 0 as x approaches 0 from the right. Same algebra, isn't it? A limit of absolute value of x over x as x approaches 0 plus, but what's that equal to? For positive values.
1.
For positive values of x, the absolute value of x is just x, isn't it? Okay. Oops, I got to write limit. I'm not going to get lazy. Because we haven't taken the limit, we haven't evaluated the limit yet, so I keep after dragging that, you have to keep dragging that limit notation along. Okay, what's the problem? They don't agree, so the limit's not defined. Do these limits make sense? Does the negative 1 and the 1, do they make sense in the context of that picture? What's going on, Richard? How come? Why the negative 1? Mm-hmm. And what about that? What about this part of the function screams negative 1 at you? What are we trying? What is a derivative equal to? A slope, right? And this is a line, so any tangent line to a line is the line, isn't it? Right? So every point over here is on a tangent line with a slope of negative 1. So that makes sense, right? As the ant is stepping towards x equals 0, from the left, he is experiencing a slope of negative 1, right? As the ant is stepping away from 0 to the right, he's experiencing a slope of positive 1. They don't agree, so you can't define a slope at that point. What do you think that graph in general represents? A function with what? This one here that we looked at previously was important because it had a break in the function. What's significant about this? This is telling us that derivatives don't exist at places like this. How come?
It's a sharp change.
It's a sharp, yeah, it's a sharp corner. Okay? Does that make sense? So we also can add to our list then sharp corner. Okay? All right. So Okay, how about last one? Let's try. Let's try one like this. I want to prove this one. Yeah, I might as well. Why not? Let's try that. F of x equals x to the 1/3. Okay, so start general, right? Our derivative, we all know this, limit of f of x minus f of c over x minus c as x approaches c. And let's take the point here, let's take the point at x equals 0. Okay? So we're going to define c as equaling 0. And let's calculate both limits then. So the limit from the left and the limit from the right. Okay, well what is f of x minus f of c in this case? Okay, so we're going to get x to the 1/3 minus 0 to the 1/3, which is just 0, right? Over x minus 0, so that's just x, as x approaches 0 from the left. Okay, so what does that give us then from the left? Actually, we don't even, on this one, we don't even have to do the left and the right on this one, I don't think. If we need to, we'll come, I can't remember. I don't think, now we wouldn't have to. Wouldn't have to. If we need to, we'll do it later. But if we approach 0, what's this going to give us? If I simplify this, what is x to the 1/3 over x to the 1? X to the negative 2/3, which is the same as 1 over x to the 2/3. So if I try to evaluate this directly, if I evaluate this directly, what do I get? 1 over 0, what's that? Infinite. Okay. Infinite. We could, if we wanted to, we could take limits from the left and the right and describe the function more accurately. But really, that's not even the point here. The point is just that we get a 0 on the bottom and a number on the top. And so that's a no limit. What do we know about that kind of no limit? What does it correspond to on the graph? An asymptote. Yeah. And if we graph that function, here's what we get. If we graph that, we're going to get something like that. The function isn't asymptotic, but the derivative is, because that's what we calculated. Explain that. Why is the derivative asymptotic here? Let's graph. Okay, go ahead.
It's the slope of the line at that point.
Ah, okay, good. Let's simultaneously, here's the graph of the function. Let's graph the derivative along with it. Okay? What's that going to look like? I'm going to graph the value of the derivative equals the slope of the function. So this is supposed to be continuing down a little bit. But what can you tell me about the slope of the function? What's it approaching over here? Okay, but not the slope.
0.
Right. It's small and positive. Agree? Like at this point right here, if I had drawn this right, why am I trying to draw it? Why don't I just graph it? Oh, this will give you an excuse to show you another feature on your toy known as Desmos. Okay, so let's graph f of x equals x to the 1/3. There it is, right? Okay. So over here, we've got a small positive slope. What's happening to the slope as we approach 0? Increasing, isn't it? Towards a vertical tangent, which is asymptote. That's infinite, right? That's an undefined slope. And you kind of get a sense now, you guys always called that no slope back in the day, but now you understand it corresponds to an asymptote in a function, right? So, or a vertical tangent in a function. So if we graph the derivative, watch this. Let's graph, down here we'll graph y equals think I can do this. F prime x. Yeah, look at that. How about that? It graphs the derivative for you. How cool is that? Right? So do you see that? The blue function is the graph of the slope of the red function. Once again, the value of the derivative function is the slope of the function. Right? Yeah.
Could you do that, but to the negative, so then we'll go on the bottom too, with like another one? Could you graph like another one so that?
Yeah. What do you mean? Like
right now.
Like, yeah, what do you want me to graph?
Like, could you do that same thing but reflected upon the x-axis?
Sure. I could graph this as y equals, well, actually, I can't. Yeah, I could. Y equals negative f of x, and there it is.
Thanks.
Yeah. Yeah, Desmos is the real deal. Okay, does this make sense, though? I really want you guys to see, if you're in physics, you've got a little bit of a leg up here, because we've done a lot of this stuff, right? I mean, when we did, in hindsight, when we did things like compared a velocity graph to position graph, what were we really doing? Yeah. What do you think is true if you take a velocity function? How about that? Did your head just go like that? Right? Isn't so? We know here now that. Where's my Desmos? Okay, so we know that if x of t, that's how we define position, right, in physics. What is v? Instantaneous velocity. Instantaneous, not average velocity in terms of x, do you think? Yeah, we'll talk a lot about this in the future. It's x prime of t, right? How about that? And acceleration? D prime of t. Ooh, we'll come back to that. Okay, but you see that that makes sense, right? The slope is getting it's really small and positive, ooh, it's getting big and positive. As you continue along, it gets less big, but always positive. Okay? All right, so this is kind of a fun game. Let's try, while we're at it, let's do this. I want you to calculate for me, I'm going to turn this one off. Just do a little sketch here. I want to know what you think the derivative function is going to look like for x squared. Okay, bust that out. Try that. Sketch what you think the derivative function is going to look like. Remember, the value of the derivative function is the slope of the function. We don't need to be. I don't need to have exact qualitatively. I don't care that the slopes are exactly right. I just want qualitatively what's it going to look like. So the value of the derivative is equal to the slope of the function. That's what the derivative means. The derivative is giving us back the slope of the curve, meaning the slope of a tangent to the curve, same thing, for any value of x. So can somebody tell me one precise value of the derivative function? There's one up here that we can definitely get exactly right. 0, 0. Yeah. At x equals 0, the slope is 0, isn't it? Because it's a horizontal tangent. Everybody agree? Okay. So we know it has to go through that point. What's the behavior going to be? What's it going to look like? Say it again, like that? Ah, you're right. That works, doesn't it? Okay, y. Let's look at y. What kind of a tangent here? Let's draw the tangents in. An ant right there sees a large negative slope, large negative tangent. So if we go directly down, we ought to get a large negative value for the derivative. as he moves along the curve, down here, well, it's still negative, but it's less negative, right? So if we go straight down, there, it's less negative. Down here, it's not very negative at all, right? The curve is getting less severe, so less negative. Right there, it's a horizontal tangent, so it's at 0, and we have symmetry on a parabola, don't we? So we get the opposite happening on the other side, right? Okay. If we look at polynomials, what's the order of this polynomial? Or the degree of the polynomial? What's the highest power of x in this one? 2. What's the highest power of x in this one? 1. Interesting. Okay. Thank you. There's a swirl file. Okay. Let's change this up a little bit. Okay. How about if we let's define f of x as x cubed, and I'm going to go ahead and make it something like 1/6 x cubed, just so it spreads it out a little bit more. Okay, ooh. So there's an x cubic function. What's the derivative going to look like this time? Make sketch. What do you got going, Josh? Do that again. I saw the universal sign for... Okay, and you're right. It's that. How come? Because it goes from being very positive slope, right? Less positive, less positive, less positive, less positive, 0, to increasingly positive. Now, I want you to notice a trend here. And I'm not going to talk about why, but I want to plant a seed here that we'll discuss as the year progresses. The red function is what degree polynomial? 3, right? How about the derivative is a second degree. So for polynomials, are you noticing a pattern here? I bet you are, right?
Can you do the f prime prime?
You can. That's called the second derivative. We haven't talked about that yet. That's a ways off. But
I just want to see it. That's going to be the line, won't it?
yeah, it will. There it is. There's a second derivative.
Oh my gosh.
Ooh, yeah, it is. So acceleration is the second derivative of position.
Can you derive that even farther?
Oh yeah, you can take a fourth derivative. So what? Okay, so what's the third derivative? What's the third derivative going to look like?
The parabola.
Okay, now the third derivative, and we're jumping way ahead here, but that's all right. You guys can do that. So we're taking the derivative of the orange line. Yeah, that's got a constant positive slope, doesn't it? Right? So we should get a horizontal line with a positive value. There it is.
And then the next one.
And then the next one would be 0, right? Because that's got a slope of 0. Okay? There it is.
Can you go any farther?
It just stays.
Well, we could, but then there'd just give you 0 from that point.
That's why I start at x to the 5th or something.
Yeah. Okay. Make sense? All right. So we can add one more thing to our list here before we get out of here today. We can add another place where functions or where derivatives are undefined. Yes, sir.
Is it at 1 because it's technically to the power of 0?
Yes, that's one way to think about it. Yeah. It's consistent with that, yeah. Okay, so we have, what did I do there? Run down a virtual link again.
The glitch.
There's the glitch, yeah. There we go. So we got breaking the function, sharp corner, what else? How would we define, what was going on there? Okay, or vertical tangent line. Yeah, vertical tangent line, which means asymptotic slope. So. Okay, so what's the relationship then? Last question. What's the relationship between continuity and differentiability? Okay, so we've got to find a new term here. Differentiability. To differentiate means to take a derivative or calculate a derivative. So differentiability is take the derivative ability, right? The ability to take and calculate to define a derivative, right? So what's the relationship between differentiability and continuity? This is an important one. It's not difficult, but it's a really important relationship. Let me ask you this. For a function to be differentiable, does it have to be continuous? It does, because you can't have a break in the function, right? Is every function that's continuous differentiable? No. For example, that one, right? Or that one, okay? So then, does it make sense that we could say that differentiability implies continuity, but the inverse is not true, right? So that's a statement we make in calculus a lot. Differentiability implies continuity. So then if I've got a function, let me just draw a random looking function up here. So where is this function not differentiable? Okay, so there, there, and there, right? Okay, how about this one? So that function is continuous but not differentiable, right? Compare that to this function, which is both continuous and differentiable. Qualitatively, what's the difference?
Sharp part.
It's got a sharp part, right? So in math, we say the combination of a function that is continuous and differentiable is, we call it smooth. Okay? So this is a smooth, literally, we call this smooth, and that is continuous plus differentiable. What are we at here? 1 minute? Oh, 35? Okay. Well, I'll let you work a little bit and ask some questions. That's probably a good place to stop. Yeah, sure. Tell me when to stop. We didn't talk about that. We'll do that other one. Well, maybe I'll just say something about it. Which one? That one or go back? Right there? Okay. Okay, so then the last thing, maybe this is something that maybe it's worth looking at real quick on your assignments. You're going to have to be able to distinguish between these four things. So a function whose graph is otherwise smooth will fail to have a derivative where the graph has this stuff going on. They broke it into more pieces than we did, but that's all right. So what corner we talked about, right, where one-sided derivatives differ. A cusp is where the slopes of the secant lines approach. So let me draw you a picture. So you can, to me, this is kind of splitting hairs, but sometimes we make this distinction. So number one looks like this. Like that, right? Number two, a cusp looks like this. See the difference? Where on one side, the slope approaches negative infinity, on the other side, it approaches positive infinity. Does that make sense? Okay, as the ant walks towards this point right here, he's experiencing, his slope is approaching positive or negative infinity from the left, and on the right, positive infinity. He goes from an infinitely steep negative slope to an infinitely steep positive slope. That's what we call a cusp. Vertical tangent, what's number 3 look like? Well, we drew one of those, right? That would be one, that'd be one like this. Right? And then, of course, a discontinuity, just a break in the function, number 4. Right? So really the thing I want to show you is these guys, we sort of call both of those a sharp corner, but there's a distinction. This is a sharp corner, but this is a really sharp corner. Right? Cusp is opposite infinity slopes. Okay. Yes, you may.